But again, could have called it whatever you want, I suppose. Okay, so that's true. We have and, or, false, not, true. And now, here's another connective that tends to be quite useful, if and only if, which we can define solely using operators that we already have in hand. So in particular, we can define if and only if to be, for two propositions, P and Q. If and only if is defined P implies Q and Q implies P, right? And we have the special if and only if double arrow notation, which uses this constant. So quick question, if I said check if, what type would I get back? Oh, there were a lot of answers. So some people said prop, some people said prop to prop to prop. The second one is the correct answer, right? Because if takes two arguments of type prop, and it gives you a proposition, right? Right. In the interest of time and AVE delays, I'm going to skip through some of these if and only if statements. You can work through the exercises on your own. And in fact, I'm going to skip over this little bit about how we can do rewriting with if and only ifs. You can follow up on that in the book. Okay. To get to our final logical connective. So we have universal quantification, as you might expect. This allows us to make statements about all possible values of a particular type. There is, of course, also existential quantification that allows us to make assertions about a particular value of that type. So here's the quantifier in coq. It exists xp. If we want to prove a goal of this form, how do we prove that there exists something such that a property holds for that particular value? Well, A, we have to exhibit a value for which that property holds, which this particular value is typically called the witness of the existential. So it's an existential that witnesses the truth of the statement. You can read it this way. So just as we had the split tactic for working with goals of type and, we have left and right for working with goals of the form. Or for exists, we have the special exist tactic, which unfortunately here, when we look at the code, we'll see it's actually just exists written out. So this special quantifier gets formatted a little weird on the slides. So when we call exists, it takes an argument. This tactic takes an argument. And in particular, the argument is the particular value that we're going to use to, we're going to show exhibit has this property. So in particular, if we want to show there exists a natural number such that 4 equals that natural number plus itself, we just need to exhibit a witness. So in this case, we'll say, well, I know what this is, 2. So once you say exists 2, it's going to instantiate all occurrences of this existential variable with the value you've given in the goal. So we'll say exists 2. Our new goal is going to be 4 equals 2 plus 2, from which we can use the reflexivity tactic and immediately finish the proof. Conversely, okay, so that's how you build, that's how you work with goals of the form exists X. What do we do if we have an assumption of the form exists X some property? Well, here we can use the destruct tactic, and when we call destruct on exist X, what do we get? Well, we get 2 new assumptions. First, we get some witness, and then we get an assumption saying that that particular value that we have, it's not a concrete value, has the property that was asserted by this in the body of this existential quantifier. So the best way to do the best way to understand this is to see it in action. So there we go. So here we go. Here, I'm going to intros here, and this should make it a little bit more readable. Oops, so we destructed a little bit too soon. Okay, so what are we trying to do here? So we get an assumption that there exists some m such that n equals 4 plus that m, and we need to show that there exists some o such that n equals 2 plus that o. So when we intros here, we're going to destruct this existentially quantified hypothesis. And this is going to give us a new variable representing the witness. In this case, we're going to call it M. And it's going to give us an assumption saying that this variable that we introduced has the property we use in the existential quantifier. So we get this h of m assumption, namely that n equals 4 plus m. Okay. So now, with this in hand, if we want to prove this goal, that there exists some O satisfying this property, we need to call the exist tactic with some concrete witness for which we can prove this fact. In this case, it turns out it's 2 plus m, the witness we got from the assumption. So once we use this tactic, we get a new goal where all of the occurrences of O have been replaced with 2 plus m. And now we just need to prove it. And this, it turns out, follows immediately from our assumption hm, or the assumption we got from destructing the existential quantifier. And if we do a little simplification here, oops, oh, that notation went wacky. Never mind, we can apply that assumption directly, and we're done. There's probably a theme you'll notice here, that when we have assumptions of a particular type, we can use destruct to do case analysis on them, and we'll get some additional information. But when we're trying to prove goals that use one of these logical connectives, there are specialized tactics for each of them. And to figure out which ones to use at any given point, it's usually dictated by the form of the goal, but to figure out what they are, you just have to use them a little bit, and then you'll get more familiar with them. Okay, those are all of the logical connectives that we're going to look at in this lecture. Now, let's look at a particular use case of programming with these propositions. So here we're going to see where some of these, the propositions we saw, like the true proposition we saw before, is going to be useful. So we now have a bunch of logical connectives, and we can imagine using these logical connectives to build up bigger and bigger propositions, right? Bigger and bigger statements, right? And that's precisely what we're going to do. So let's think about how we might use these connectives we've seen to define the property. There is some element that occurs in a list L, right? So when can an element, when is it the case that some element occurs in a list, right? Well, if L is the empty list, this can never hold, right? So the property, in the case that L is the empty list, X appears in L is always false, right? Otherwise, if this list is some value appended to some sublist, X is going to appear in that list, either if it's equal to the head of the list, or it appears in the tail of the list, right? Now, what's so nice about these propositions being first-class objects is that we can actually work with them programmatically, right? We can define functions that will produce statements. So in particular, we can define a function that will produce a statement that is equivalent to X is the element of a list. And here is precisely that function, and its definition follows exactly these two cases we saw up here, right? So look at this fixed point. So this is a fixed point. It's going to take some type of the list. It's going to take some element of that, some value of that type, and it's going to return a proposition, right? This is just like as before we defined this is3 or is3 proposition, right? Only now it's a little bit more complicated because we're going to define this recursively. So what are we going to do? We're going to match L. In the case that L is the empty list, well, this could never hold, so X could not be an element of the empty list. Otherwise, if we have this cons case, either X prime is equal to this element, right, if X is in the list, or X must be in the sublist. And if you can imagine, for any particular list, right, we can run this function and produce a statement asserting whether or not an element is a member of that particular list. So, yes?
Sorry, probably you answered before. Why is it useful here to have prop instead of bool? Because in
yes.
you would do it with bool.
Can I revisit that question? It's coming in a little bit, okay, right after this. Yeah. I think it is, sorry, the question is why did we use bool, prop instead of bool to define this, this lemma? And the answer is we'll see why in a little bit, which is a little unsatisfying. But to see an example of this definition in action, of list membership in action, we have down here this proof statement. So here we're saying we're trying to prove a lemma, and we construct the statement of this lemma programmatically, right? So here we have this in function. It's defined recursively over this list. And here's the element we're checking membership of, checking the membership of. So if we do simplification, what is it going to do? It's going to expand the definition of that function over that concrete list, right? So we're going to get this long sequence, this long disjunction of the particular element we're looking for, in this case 4, is equal to each member of the list, right? Now to prove this, we can just use our tactics for working with goals of the form or something, right? So here, well, 1 is clearly not equal to 4, so we're going to go on the right-hand branch. 2 is clearly not equal to 4. But now, 4 is equal to 4. We'll go left, and we can prove that immediately. So now we've established this proof, which is, this is pretty cool, right? We've defined a function that will give us a statement, just generically, and we use that to write a proof. It's pretty sweet. Are there any questions about that? Yeah.
Well, in this particular case, you only have constants and equality is decidable. I suppose you could have some kind of tactic that automatically discharges for you.
Indeed, you could have a tactic that just discharges this automatically. And there is, in fact, a tactic in coq's standard library that will solve this goal immediately. And we will see an example of that tactic in use, I think, on Wednesday. But yes, that's exactly right. Yes?
Is this, maybe you already said this and I missed it, but the equal sign in these expanded disjunctions, that doesn't have computational content.
That's exactly right. So the question was, does the EQ used in this statement have any computational content? And the answer is no. There was yeah. So EQ is just another definition, another way, it's another inductively defined proposition that represents equality. And it lives in prop, and since it lives in prop, it doesn't have any computational content associated with it. Yes?
So we use prop for things we do not want when we obtain algorithms. But what if I want to say, hey, X belongs to this list, here's a proof, and from the proof, you can get the exact location. And so the indexing algorithm is correct because it's extracted from the proof. So how do I disentangle the proof and the index?
The question, to restate the question, was, okay, suppose we did actually want this proof to be computationally relevant, and we wanted to be able to extract sort of the index of a particular element in the list from this proof that we wrote here. The answer to that question is we would have to move the definition of this m, the definition of n from prop to type. That's it. So there's, yeah.
So if we just change that line from prop to type, we do that? Top line?
In some sense, yes. Yeah. Yeah. Are there any other questions? I might as well just step through this one last example of using n and existential quantifiers. So here, again, we're going to use n on a particular concrete list. So this is a little bit more interesting because now instead of working with a concrete element of the list, right, we're going to assume that for some arbitrary n belongs to this list. So what does this look like? So after we do simplification, we see we're going to have 3 assumptions, right, from the definition of this predicate, just expanding this proposition just by expanding it out. So if 2 was an element of this list, it must either be the case that, if n was an element of this list, it must either be the case that n was equal to 2, n was equal to 4, or false. Okay? So when we impose these goals, what does this mean? So we get to assume that either 2 equals n, 4 equals n, or false. In the case that it's false, the goal follows immediately. So when we destruct that, it disappears. And now we just have these two goals. So now we have the case that n equals 2, and we can exhibit a concrete witness, right? In this case, let me make sure. Yes, it's 1. So we say 1, we replace all the occurrences of n prime with 1, and then we can rewrite with this equality and the equality assumption. Reflexivity solves goal. We can exhibit, similarly, the witness 2 for n prime. We can rewrite with our assumption, and then we're done. So, man, it's so cool. The idea that propositions are first-class objects that you can generate programmatically and manipulate, it's just a powerful idea, and you'll be seeing it in action quite a bit as the week progresses. Okay. We can also prove more generic, higher-level lemmas about n. In particular, right, so if we have instead of working over a concrete list, maybe we can prove something for all lists, right? We don't have any concrete lists in hand. How might we do that? Well, here's an example. So here's this in-map lemma. It says that if x is a member of a particular list, then it must be the case that applying a function, it must be the case that f of x is a member of mapping this function f over that list, right? So how does this proof work in action? So we're going to do induction over the list, and by doing induction over L, we're going to get two cases. One where L equals nil, and one where L is equal to the cons of something, cons of a value onto a sublist, right? And once we replaced L with these concrete values, now we can evaluate the in predicate, right? So in the case that L equals nil, we have this in assumption, right? And n, when L is nil, immediately becomes false. So we can just discharge false immediately. This intros is just destructing that false assumption. In the other case, where L equals x, where the list is some value const onto some sublist, right? Now we can again evaluate n, and there are going to be two cases. There's the case where I guess x is equal to the first element of the list, x prime, and then there's going to be the case where x is an element of the sublist. So we can evaluate that out. We're going to get two cases. We have an or, and we're going to split them. In the case that x is equal to the head of the list, we can do some rewriting and apply the or the tactics we have for working with ors. In the other case, we can, in which x is an element of the sublist, well, now we can use the inductive hypothesis, and again, apply our assumption about x being an element of the sublist. It's probably more helpful to walk through this in the proof buffer. So I encourage you to do that on your own time. Okay. Let's see. We've got 10 minutes left. Are there any questions about n? Or this idea of programmatically generating proof propositions? Yeah.
Here, first class is similar to first order, like.
No, that's not. The way to think of first class is that it is a distinguished object of the language that you can treat as data, you can pass around as a value, you can manipulate. Okay. Because even if it were a higher order function, that higher order function is itself a first class member of the language that you could pass around. I know it's a little confusing. Yeah?
We'll have props between functions.
Can you have a prop between functions?
Lambda equals number lambda.
So you're asking lambda equals lambda lambda. Yes, you can assert equalities hold between two different functions. So you could, yeah. And indeed, we'll see an example of that a little bit later in this logic lecture. Are there any other questions?